Greetings, Sir Cleopas and fellow classmates. We are the fourth group and we are going to present the fifth experiment, the extraction of crude caffeine from tea using liquid-liquid extraction.
This presentation has been split into four parts. The first part being the introduction, which answers the questions, what is liquid-liquid extraction and how will it extract caffeine? The second part is the materials and methods and what are the materials needed for the experiment and how will it be conducted. The third part is the resultant discussions, which answers the questions how much caffeine was extracted or why was the caffeine extracted. For the last part, summary, conclusions, and recommendations. These answer the questions which of the solvents and techniques were found to be more effective and what can be done to improve the experiment.
For the objectives of the experiment, first is to isolate crude caffeine from brewed tea by liquid-liquid extraction using hexane and diethyl ether extracting solvents. Second is to compare the extraction efficiency of the two extraction solvents. And lastly, to compare the extraction efficiency of crude caffeine by single and multiple extraction.
What is liquid-liquid extraction? Liquid-liquid extraction, also known as solvent extraction and partitioning, is a method to separate compounds based on their relative solubilities in two different immiscible liquids, usually water, which is usually polar, and an organic solvent, which is non-polar. There is a net transfer of one or more species from one liquid into another liquid phase, generally from aqueous to organic. In this experiment, organic solvents, namely hexane and diethyl ether, will be used to extract the organic components of caffeine from tea. Tea is one of the most commonly consumed caffeine beverages in the world. Caffeine is a naturally occurring compound found in plant species and is one of the most widely used psychoactive substances in the planet. What is caffeine? The caffeine found in tea, C8, H10, and 4 O2 is a bitter, white crystalline methylxanthine and a member of a class of compounds known as alkaloids. Alkaloids are a huge group of naturally occurring organic compounds which contain nitrogen atoms in their structures which are present in plants. The structure of caffeine affects the functions it performs. Alkaloids happen to be extremely important for human beings and other living organisms for ages. With this, extraction of pure caffeine is needed and vital in order to utilize its effects and use it as a component in different products. In order to extract caffeine from tea, several methods are used. First, a solid liquid extraction must take place in order to get the solid natural product into the liquid solvent. This can be done by using stock split extractor or by just brewing a cup of tea. In order to separate the desired reaction compounds from the natural product, liquid-liquid extractions are used. In this case, as I said earlier, organic solvents, namely hexane and diethyl ether, will be used to extract the caffeine from tea by means of liquid-liquid extraction, which allows the isolation of single components from a mixture. Alongside this, the extraction efficiency, which is the percentage of solute that moves into the extracting phases, that is determined by the equilibrium constant for the solute partitioning between the phases and any other reactions involving the solute of those two extraction solvents and between single and multiple extractions will also be compared.
For the materials and methods, the following are the materials and equipment utilized in conducting the experiment. And now for the procedures. 90 ml of distilled water was added to a 150 ml beaker and 9 grams of sodium carbonate until it dissolved. Then a wooden boiling stick was added and the solution was boiled. The beaker was then removed from the heat so as the boiling stick, then a tea bag was added. After the solution was cooled down to a comfortable temperature, the water was squeezed from the tea bag and a spatula or glass rod was used as a support. The brewing process was repeated twice, but new tea bags were added. Hence, a total of 3 tea bags were used. Then a 20 ml of brewed tea was transferred to 4 125 milliliter separatory funnels and were cooled below 40 degrees Celsius. Afterwards, a 12 ml of ether was added to the extraction solvent on one of the separatory funnels and was cupped. In a fume hood or well-ventilated area, the funnel was shaken gently several times, and in between 1 to 2 seconds periods of shaking, the funnel was inverted and the stopcock was twisted and opened slightly release the excess pressure from the separatory funnel. The separatory funnel was then hung right side up in an iron ring, and the layers were allowed to separate. The organic layer was then determined through a drop test, wherein a drop of solvent was added to identify in which layer the drop dissolved in. Then two 50 ml beakers were prepared, wherein one contained calcium chloride. The organic layer was collected into the beaker with calcium chloride, and the aqueous layer was later discarded. The beaker was swirled, and more drying agents were added when the calcium chloride clumped together. The mixture was filtered into a pre-weighed Erlenmeyer flask to remove the drying agent. Then it was cleansed with minimal amounts of solvent and filtered through. The solvent was then evaporated using a warm bath with a water temperature around 70 degrees Celsius. Then the yield of caffeine was determined and the extraction was separated, but only two portions of 6 ml rather of solvent were used, and the yield was compared with the previous result.
For the results of the experiment, this table shows the amount of caffeine extracted using diethyl ether and hexane in single and multiple extractions. The maximum yield for each extraction is approximately 135 milligrams of caffeine, as there are 3 bags in each extraction, and each tea bag contains approximately 45 milligrams of caffeine. As seen in the table, the yield for each extraction are as follows. 100.4 milligrams or 74.37% of the caffeine was successfully extracted in the single extraction for diethyl ether. On the other hand, the multiple extraction yielded 80.7 milligrams or 59.78%. For hexane, 62.1 milligrams or 46% of the caffeine was successfully extracted. The multiple extraction for hexane yielded 122 milligrams of caffeine or 90.37%. For the discussions, to extract caffeine from tea leaves, solid liquid extraction is done by boiling tea bags in water to create a solution. The caffeine in the solution can be extracted using an organic solvent in liquid-liquid extraction. In this experiment, hexane and diethyl ether are used as they are immiscible with water. Since the extraction solvent is less dense than water, and an organic and aqueous layer is formed in the separatory funnel when the solvent is added. Most of the solute, the caffeine, transfers to the organic solvent. How much of the caffeine transfer depends on the polarity of the solvent. Since hexane is nonpolar due to its symmetrical structure, the diethyl ether is much better solvent since it is a polar molecule. The polarity index of the two solvents is seen on the table on the left. The polarity index for diethyl ether is 2.8 while it is 0.1 for hexane. This proves the claim that diethyl ether is a better solvent. The yield results for both hexane and diethyl ether in single extraction also prove this claim.
Theoretically, liquid-liquid extraction is more efficient since the goal of extraction is about maximizing surface area contact between the two solutions. There will be more surface area contact with smaller volumes like in the figure shown. Furthermore, you can mix two smaller portions faster and more thoroughly than with large portions. When extraction is done, the residue will have the same concentration of material as the extract itself. If extraction is done in the following time, the extraction will be lower in the extract as well as in the residue. So with multiple extractions, the amount of material left in the residue will be lower, hence the extraction will be more complete, which increases the extraction efficiency, like in the illustration.
Based on the results obtained in the extractions made with the use of hexane, it clearly showed that the use of multiple extraction technique resulted in a much higher extraction efficiency. However, the same could not be said for diethyl ether extractions, as there was more caffeine extracted in the single extraction than in the multiple extraction. A possible explanation is that there was an error in the procedure, such as the tea bags not being squeezed enough, emulsions, or the caffeine molecules being left in the beakers.
Sodium carbonate was also used in this experiment. It serves two main functions: to place caffeine in a more basic environment so that it has a higher affinity for the organic solvents, and to cause the tannins to form phenolic salts in the aqueous solution. Adding something basic to the caffeine will make it more neutral, and the principle like dissolves like can be applied. Sodium carbonate, which is a base, deprotonates or removes the proton of a phenolic hydroxyl group or the OH group of a tannin, which is acidic, making them anionic and it converted to phenolic salts. The caffeine, on the other hand, remains a free base. If sodium carbonate is not added when extracting caffeine with hot water, the extracted caffeine would also contain said tannins. Additionally, sodium carbonate is added during the extraction to keep caffeine, an alkaloid which is an organic base, in a free base form. It prevents caffeine from reacting with available acid, which may lead to the formation of cations. It reacts with phenolic hydroxyl group of tannins, thus maintaining them in aqueous phase when the liquid-liquid extraction, is performed. This experiment also tackled emulsions, which is a combination of two immiscible liquid, which is two immiscible liquids in which one of the liquid is dispersed as small droplets into the second liquid. Formation of emulsions with the extracting solvent can be avoided by swirling separatory funnels gently instead of shaking. It reduces the agitation that would cause the formation of emulsions. However, the surface area of contact is still maintained between the two phases for the extraction to occur. If an emulsion has already formed, it can be disrupted by adding brine or salt water that increases the ionic strength of the aqueous layer and separates the two phases. It can be separated through filtration via a glass wool plug, which removes the emulsions, or a phase separation filter that isolates a specific layer. It allows either aqueous or organic phase to pass through and be isolated. Moreover, the addition of limited amount of different organic solvent, which alter the solvent properties of the separation, which could result in a surfactant-like molecule which breaks the emulsion. Additionally, it is important that the tea solution is free from proton sources. Since caffeine is an amine, it contains a nitrogen atom that will react with a proton source such as hydrochloric acid to produce an ammonium ion, a salt which is water soluble. A water-insoluble amine will regenerate after a base is added to the acidic aqueous layer as seen in the figure. This experiment also tackles distribution coefficients. In liquid-liquid extraction, a partition coefficient or a distribution coefficient exists. This is the constant ratio of a solute in each layer when the partitions between the solution and the immiscible solvent have reached equilibrium. This distribution coefficient can be used to calculate percent recovery. This distribution coefficient may be represented as KD and is the formula seen in the figure on the left. The formula per percent recovery using distribution coefficient is also seen in the figure on the right. The VAQ, which stands for the volume of the aqueous solution, is divided by the KD or distribution coefficient and multiplied by the VORG, which stands for the volume of the organic solution, plus the VAQ, and the whole equation is raised to the number of extractions. This equation will give you the QAD, which stands for the fraction left in the aqueous solution. This is subtracted to 1 to get the fraction left in the organic solution, which can be multiplied by 100 to get the percentage. As an example of getting the percentage recovery using the distribution coefficient, given a 50 ml saturated solution of caffeine, the percent recovery of caffeine in single extraction using 20 ml of DCM or dichloromethane, and the percentage recovery of caffeine when the extraction is done twice using portions of 10 ml DCM is determined at the figures presented in the slide. The distribution coefficient of caffeine between dichloromethane and water is 4.6. In the first computation, it is seen that the percent recovery of caffeine in single extraction using 20 ml of TCM is found to be 64.8%, while the computation for the multiple extraction, which is extraction of the 2 times extraction of 10 ml DCM, is found to be 72.9%. This also proves the theory that multiple extraction is theoretically the more effective way of extracting.
In summary, the liquid-liquid extraction method is a process that isolates a single component, which is the caffeine, from a mixture, which is the tea, wherein the tea was brewed and the caffeine was separated from the water-soluble pigments by squeezing the tea bags until there are no traces of water. The following are the different solvents used in the experiment and their amount of extracted caffeine. For the diethyl ether, on the single extraction, using the single extraction, 100.4 grams of caffeine was extracted, and for the multiple extraction, only 80.7 of grams of caffeine was obtained. Then for the hexane single extraction, 62.1 gram of caffeine was extracted, and for the multiple extraction, 122 grams of caffeine was extracted. Using the data, the yielded extraction was calculated, and we obtained the results that the single extraction diethyl ether yielded a higher amount of 74.37% than the hexane, which is only 46%. On the other hand, multiple extraction diethyl ether yielded 59.78%, which is lower than the 90.37% of hexane. It can be concluded that the solvent diethyl ether in single extraction obtained the greatest amount of extracted caffeine. Therefore, it is the more efficient solvent. Moreover, none of these solvents gain 100% recovery since there is material loss during the transferring of substances in the procedure. Hence, the loss of product is one of the possible occurrences in the experiment, which can also be caused by emulsions, human error, and or because of unthorough cleansing of solvents to extract as much caffeine as possible. The theoretical amount of caffeine in tea bags could also be a source of error and could result in invalid data or the different calculation on percent recovery. Also, it is recommended that precautions must be taken into consideration to avoid errors such as the miscalculation or misrepresentation in the data acquired in the single extraction of diethyl ether, which had a higher yield compared to the multiple extraction.
And that is all for the experiment number 5, which is the the extraction of caffeine using liquid extraction. Thank you po.
Thank you.
Thank you.